Okay, hello again and welcome in today's lecture, which is about groundwater. And I will try to cover two lectures about groundwater. First lecture is in general. I'm going to explain Darcy law, and in the next lecture, I will try to talk about aquifers and different kind of aquifers that we have. Okay, but before starting this lecture, let me ask a question. If you remember, in the second lecture, we talked about the amount of water distribution in space. Do you remember, does anyone remember the percentage of groundwater that we have as a fresh water in the world?
30%.
Yes, 30%. Thank you, Arda. And what do you think about other potential or other available freshwater resources? What is the biggest one? The biggest freshwater resources? Do you remember?
The glacier water.
Yes, yeah. Thank you. Glaciers. And how much is it? How many percentage?
The total is 70%, sir.
Yeah, more or less about 70% of the fresh water in the world available in ice caps and glaciers. Okay, let's come back to our course and let's start with a short review of what we studied in previous lecture, which was about infiltration. In previous lecture, we defined infiltration as the process of water penetrating from the ground surface into the soil. And I said that the maximum rate at which water can enter to the soil called infiltration capacity. Then we saw some basic definitions that relevant to the infiltration, and one of them was porosity. You remember that we said that in addition to some important factors like precipitation rate or vegetation or green cover on the soil, porosity is one of the important factors that influence the infiltration capacity. And here you see two different materials, a sponge and a clay brick, and it shows that porosity, which we already defined it as the percentage of open spaces or voids, we said voids, which covers the air and also fluid liquids in the soil sample, is called porosity. Mathematically, we said porosity is the volume of voids over the total volume of a soil sample. Here you see that a sponge has a higher porosity, a brick has lower porosity. Therefore, in which one we will have higher infiltration in your mind? Yeah, if here is written also, if you have greater porosity, therefore more water can infiltrate into the soil sample. Therefore, in sponge we will have higher infiltration rate. We also talked about soil moisture content, and we defined it as the volume of liquid water to the volume of water. You remember that we represent porosity by theta, and we said that soil moisture content or theta is always between 0 and eta, and when the theta is equals to eta, it shows that the soil sample is completely saturated and all the voids, all open spaces fulfilled with water. Okay, so after that we talked about Vedas zone, and we said that when water infiltrates into the ground from surface, it tries to move downward actually to reach to the saturated zone, which is called groundwater. And today we will talk about this zone actually. And previous lecture we talked about Vedas zone, and we saw that in the Vedas zone, for example, we have negative pressure. We talked about water table, that is the boundary between Vedas zone and Vedas, also called unsaturated zone. And water table is the boundary between Vedas and saturated zone. We also talked about capillarity fringe, which is the zone that water moves upward to the capillarity effect of tiny pipes that are available like this. You see, this is a tiny pipe, for example, here, this here, from here to here. You remember my cursor? This looks like a pipe, yes? And because of the capillarity effect, which is as a result of surface tension between soil and water moves upward, and therefore we have an upward fringe or upward region. It's very actually short region. So it is called capillary zone. And then we took the field capacity and wilting point. You see here an example of soil sample when it is saturated, and if you rain on it again, extra water will drop down, and you will actually after a while also there is a water into the sample due to gravitation. We will not they will not be dropping water, and water remains in the soil sample, and it is the sample that has its full field capacity, or we say field capacity. When the water, this water is a water that is used by actually in this Veda zone by root of trees, plants to grow the trees, and this water is exposed to evaporation process, and you know due to evaporation and also use of plant trees, the amount of this water could be decreased, and in a way that in a situation that, or in the time that we do, the water available, or the moisture, we can say moisture available in this soil is not usable by roots of plants. We say the sample is in the wilting point, and in that case we have to irrigate the system soil again in order to provide water to the plants. Okay, so we talked about when we moved from here to here, we lost amount of water. It is possible that we should provide some amount of water for this sample to reach to this condition, to achieve this condition again. Those amount of water here is called soil moisture deficit, or this represents the amount of rainfall. Actually, when I say we should produce water, I mean the water in the nature is rainfall water, precipitation, which is necessary to return the soil to the field capacity. It is called soil moisture deficit. Deficit means shortage. And now I will just talk about a bit about the Darcy law, then explain in detail. Darcy law is a law that we use to calculate flux of water and also to calculate the net velocity of water in the saturated soil. You see the formula is given like this. This Q is called flux. Okay, this is not discharge, it is flux or Darcy flux equals to K times SF. SF is actually shows head loss, this term, head loss, or it is something like slope in fluid mechanics, slope of the head loss, or let's say head loss divided by to the length of this, the soils that water moves, and this shows the discharge. And K is a parameter, it is a parameter which is called hydraulic conductivity. The unit is millimeter per second. And the reason, and due to the such a head or such an energy that we have P over gamma and Z, I talked about these terms in fluid mechanics previous lecture, but you remember that from that course, you might know that energy has three terms in general. In moving water bodies, one of those terms is potential energy, or Z, which is the energy due to position of an object or a position of a water body. We have also in water or liquids, we have pressure energy. Because of the pressure, we have also pressure energy, or pressure head is here. And also we have kinetic energy that you don't see the kinetic energy term here. Kinetic energy is V squared over 2G, and V is the velocity. And as you know, the velocity of water in the soil is too low, and the kinetic energy is really negligible. Therefore, generally, when we talk about total energy in soil, we neglect the V squared over 2G term that we have as a kinetic energy in energy equation or Bernoulli equation in fluid mechanics. So if you use this equation to calculate flux, you can divide it by the porosity, and then you can find net velocity. Because when we say water infiltrate or liquid moves into the soil, it does not move through this solid particle. It moves through the voids, through the open spaces. Therefore, velocity, when we are going to find velocity, we divided the flux to the area of the voids, not total area. And this is why we say we use eta, and the result is called net or effective, effective or pore velocity in soil. Okay, definitely these are new for you, but in this lecture I will talk about more about how we derive Darcy law and what is the experiment behind that formula. Here, here you see the experiment of Darcy. This is our groundwater layer. This is water table, yes. Here we have vadose zone, unsaturated zone. This is a saturated zone. And I have two piezometers like those, or these are called wells, observing wells or piezometers that we talked in fluid mechanics. And the distance between two piezometers is 1 kilometer. And if here is the this point shows water label here, water table here, maybe this is the elevation of the screen of or lower part of this piezometer. And the question is how we can, and we see that water moves from here to here. Actually, you see that water elevation at this point is higher than elevation at this point, and the difference is 1 meter. Therefore, we can say that water moves in the ground in the saturated zone from left to right. And the question is, what is the velocity of groundwater, or velocity of water when it moves from here or here? we can ask this question like this. For example, one molecule of water, if one molecule wants to move from here to here, which is distance is 1 kilometer, how many hours, how many days, maybe how many years, months, we should wait that molecule arrives here. And this question was answered actually by Darcy, and I will explain how he answered this question. But before going to explanation of Darcy experiment, let me ask a quick question from you, because we are talking about motion of liquid in soil. Yes, motion of liquid in soil. Our aim is to calculate the velocity of that motion. So my question is this: by law of nature or naturally, water flows from high to low. Each of these multiple choice is correct. By law of nature, water flows from high to low elevation, from high to low energy, from high to low pressure, or all the above options are true. Do you have any opinion about it? Can you guess which answer is correct? I gave some explanation in previous lectures. Maybe you can find the answer. If you don't, if you are not sure about your choice, after this lecture you will get you will be sure which one is true. And I don't know that I can answer just. It is better to answer just now or continue, and you will find the answer during the lecture. Let's see this experiment, which is done in, I think, in Utrecht University. And here we have a model of a soil, which in a laboratory, this soil sample is under the rain. This is a rain. Assume this is, for example, 1 meter in height, 2 or 3 meter in length, and there is 2 ditches, 1 ditch here, or let's say stream or river, and some of the water moves in those. These are glasses, actually. These are glasses, and in the nature they can be ditch or rivers. Another one is here, and from the back of this panel, they inject dye, some colorful liquid, some red liquid into the soil, and we know that after rainfall we will have infiltration. Okay, infiltration, and this sample is it could be sand. We have 2 parts of clay very, the clay has low porosity, and maybe the motion is of the infiltration is impossible in that area. Therefore, by monitoring the motion of this red liquid in this sample, we can find where goes this red liquid. Here you see that the red liquid which injected from back of this panel from here it first moves downward, comes downward, but then it moves horizontally, and the liquid founded a more porous area between 2 clay layers, and then moved here until liquid moves from here upward to reach the river. And you see that also there is no injection of red liquid into the ditch. It just receives rain, but it gets red and red by the time that this ditch also gets red. Therefore, it seems that some of the this red liquid infiltrates or moves upward from the soil into the river. The other, look, there is another, for example, you see there is another entrance or liquid injection point here, and in this here you see that liquid moves another pass. This is the pass line of this liquid to achieve the here. And also we have some the color this stitch, but lower amount, but lower or a lighter color than this, because maybe this injection just infect on this stitch, but this one also this is the only injected liquid that moves into this one. So from here I want to get a conclusion. You see water moves from higher elevation than lower elevation. You remember we said always we assume a datum. For example, the bottom of this panel can be our datum. Here has a higher elevation and here is lower elevation. Therefore, water by the nature of water flows from higher elevation to lower elevation. Therefore, this answer A, option A, could be correct. So, but here you see that water moves upward from lower elevation to higher elevation. Therefore, this could not be the only answer. There is another, maybe another or some other factors important. Why do you think water moves from here to here upward? Definitely, you know that, for example, when water moves upwards, energy at this point is higher than this point. Therefore, it could push the water moves upward. And therefore, the energy could be a correct answer also. How about pressure? Is it important at the motion? Yeah, it is a part of total energy. In the previous lecture I talked total energy, we have pressure energy also. Therefore, all the answer, or option D, is correct. All the answer is true. You see the motion downward, horizontal, upward. And why pressure alone is not important? Because if you remember from hydrostatic, for example, we have higher pressure here, yes? If you remember, going downward into the liquid, pressure increases. Atmospheric pressure, we have just atmospheric pressure at the top, but at the bottom we have atmospheric pressure plus gamma of this liquid times the height of the liquid. Therefore, at the bottom of this cylinder, we have higher pressure, but there is no motion upward. This is a body of liquid at rest. Therefore, also we have higher pressure here. There is no motion, because no motion from down to up because of the energy. Therefore, in order to say that, we can generalize this answer as energy. As energy covers elevation, you remember Z term in energy equation covers P over rho G pressure term. Therefore, the correct exact answer is energy. So water moves by the law of nature. Water flows from high energy to low energy. So let's come back to the definition of energy in soil and liquid. We said that this is, for example, Vedas zone, okay, or and we are looking at to find what is the energy of what the soil sample at this point. We put a piezometer here, and we will see that water can move up to this elevation in the piezometer. This is called actually pressure head, and we have also elevation head. Here in soil mechanics or hydrology, the term head is used But this is just equivalent to the energy or hydraulic energy, elevation energy, or for the elevation energy, we said potential energy, and pressure head or pressure energy. And therefore, the sum of these two terms is called hydraulic head. H is called hydraulic head that summarize total energy of soil in that point. Hydraulic head equals to Z plus P over rho G. Z is elevation head, OG is potential head. You see, you remember Bernoulli equation, that is total energy. We said Z plus V square over 2G plus P over gamma. This term is this one. And Z is the same elevation, but we don't use kinetic energy term because I told you velocity is negligible. Therefore, we can assume V is equal to 0, and we can show the total energy that is the engine for the motion or flow of liquid in the soil equals to elevation head plus pressure head. Yes, this is called hydraulic head equals to elevation head plus pressure head. So this shows that information shows energy in one point. But in order to calculate velocity or answer the first question, what is the velocity of motion of water from one point to other point, which was 1 kilometer distance between 2 points, I need to know energy at both points, and then I can say yes, if energy is higher or hydraulic head is higher at point 1 in comparison to point 2, therefore water or liquid will move from 1 to 2, and vice versa. If the head or total head or hydraulic head is at the point 2 is higher, therefore water moves from higher energy to lower energy. Here let's see which is correct. At point 1, this is my point 1, for example. Here is my point 1, sorry. This is my point 1, this is my point 2. And I put piezometer here, and I saw that water comes up to here. Actually, this is water table. When you put a piezometer in a weighted zone, the water can come up to the water table. And this is why we say it is observing well, maybe, because observing well shows the level of water table. Okay, so here the total hydraulic head equals to this amount, or Z1 plus this amount, which is equal to pressure at here over the gamma of water. Here at this point, Z plus this value, and you see that in general hydraulic head at point 1 here is higher than hydraulic head at point 2, which is H2. Therefore, we can say that water moves from here to here. And so what will be the velocity? This black line here shows Z equals to 0, which is our datum or reference line. Okay, so here we can say that, as I told, water moves from here to here. And you have a well, a real well here, and it shows that by the time, if you actually use for example, extract some water from well, pump well out, after several days, for example, you will see that, okay, water elevation comes back to be the same. Why? Because of this motion, because of motion of water from the surrounding zone to the well. Because when we are far from the well, you see, this is water table. When we are far from the well, moving far from the well equals to increasing the hydraulic head. Therefore, water always in this system, water moves to the well from, for example, in this part from left to right, in that part from right to left, and it shows how water moves horizontally. But this is another example. This is another example that I put two piezometers so close to each other, but at different elevation. Here you see this line. Let's show maybe this. You know, these two point piezometer are at the same elevation. Their screens or their bottom are at the same elevation. But I have distance here to here. They are not at the same elevation. They are so close. And now we are interested to find if water moves upward or downward. Okay, if water moves upward to downward. How we can find it? Just by checking the water level in the piezometer. In this piezometer, I see that water is here, but in the next one, water is here. So I can say that water moves from up to down or downward seepage. I have seepage or infiltration is downward because this one, which is higher, shows higher hydraulic head. And in this example, which may be in another location, I see that water in the piezometer at this one, which it's Z term. This is Z. Yeah? Here from here to here is Z for this one, and from here to here is Z for this piezometer. The head in this one is higher, therefore water moves from here moves upward because energy at here is higher than, or hydraulic head is higher than here, therefore it is called upward seepage. So either horizontal or upward seepage, how we can calculate velocity of that seepage, and also its amount. And to answer this, we should review the Darcy's experiment, which is explained here. You might have seen such experience in your soil mechanic course, but let's review together. I have a soil sample in a cylinder. This is my soil sample. The situation shows this is saturated. And from here to here, I have two filters. You know, this is a filter that does not allow, for example, sand moves out of this sample. The area of the cylinder is this circle. I have such a circular area for the cylinder. Area is A. And water moves from left to right. Direction of flow is shown here. Water moves from left to right. Why? Because you see hydraulic head here is higher than hydraulic head here. From where you can see from this, actually, if you put a piezometer, this is actually one piezometer. It could be a piezometer that shows hydraulic head at this part or section 1, either. This piezometer shows the hydraulic head at this section 1, and this is another piezometer. This is another piezometer that shows hydraulic head at section 2, and you see hydraulic head at section 2 is H2 because from here to here, for example, is Z1, and from here to here is my P1 over gamma pressure head. Because at X1 hydraulic head is higher than hydraulic head at X2, therefore direction is to the left to right. Now I open the valve and I allow the water comes into the system, and I know that what comes, and if the system is saturated, should goes out from here. What comes in should goes out from this piezometer, and by measuring the water goes out, I can understand how much is the discharge or flux of water in my sample, because what goes up from here should pass from here to here, and therefore the discharge from releasing water is at hand. Okay, here you see the also the distance, how much hydraulic head at section 1 is greater than hydraulic head at section 2. The answer is this delta H, and this is the value, and delta H. This is H1 is higher than H2, this amount. Or actually, why it is negative? Because commonly we say H delta H equals to H2 minus H1. Therefore, H2 minus H1 will be negative, and delta X, which equals to X2 minus X1, is this value. If you say this is the coordinate is 0, the length of soil sample, the length of my soil sample should be considered as delta X. Okay, so what by monitoring this experiment, what did Mr. Darcy, we will see here. Okay, Darcy said that if I increase or change the value of this delta H, if I change the delta H, or if I increase the length of this piezometer, what will be happen? Or he said that what would be happen if I enlarge difference between hydraulic head? How it can be enlarged by increasing the H1 or decreasing the by increasing the length of piezometer 1. Anyway, by increasing delta H, by increasing, what will be happen? What do you think? Discharge will increase or not? Discharge passing the soil sample. He saw that yes, by increasing this will increase the discharge, and naturally it is correct. Then what he did, okay, let me change the length of my soil sample. And instead of having such a long sample, he assumed a shorter one. And in other words, he decreased the delta X, He said, if I decrease, what will happen? What do you think? If we decrease delta X, discharge increases or decreases? What's your opinion? Naturally, by decreasing delta X, discharge will increase, because you know this is this part of this system tries resist motion, resist fluid motion, and when your sample is smaller, therefore, for example, instead of having sample from here to here, I have such sample from here to the half of it. Therefore, water can easily move forward in the remaining part, and therefore the discharge will increase. And then Darcy also considered variation of cross-sectional area. If cross-sectional area increases, what will be happen? At least you should be able to answer this one, yeah? If you increase the area, or you use a bigger pipe, bigger cylinder, what will be happen? By increasing the area, you know, the voids, sample voids or space will increase, and therefore we know that discharge will increase. We also know that Q equals A times V, yes? A times velocity from fluid mechanics. If A increases, Q increases. Also, this A is area of entire sample, but we know that when you increase the area, the void area increases and Q increases. So if we consider the relationship between these change, we can say that discharge passing this sample is linearly linearly proportional with the increasing of the delta H, increasing of delta H. It is linearly proportional and linearly directly proportional with the area, but adversely proportional with the increasing of the delta X. So, because when you decrease it, discharge increase it. Therefore, we put it at the denominator, and so we will reach such a equation. Q equals to, Q is proportional with H1 minus H2 divided by X2 minus X1 times area. So this notation or this expression is a bit strange because the numerator is H1 minus H2, but in denominator we have X2 minus X1. It is better or more user-friendly to replace the location of H1 with H2, and it should be similar to X2 minus X1, and we can easily say delta X because delta X is equals to H2 minus H1. So by replacing their location, I have to multiply this fraction with -1. Therefore, my new equation is like this. Q equals to delta H over delta X, or H2 minus H1. What is the H2? This is hydraulic head at section 2. H1 is hydraulic head at section 1 times area divided by delta X. Look, H2 minus delta X is this value, yeah? And X2 minus X1 is delta X, this value. You see that I'm dividing these lengths to this length. Therefore, it gives me some angle, like some angle, or tangent of this theta could be delta H or over delta X. Okay, instead of tangent of theta, because I don't know actually theta it's not at hand, I can say, okay, this is called the term I. I shows this rate of, this is a rate of increase, because when I'm here, delta H, when I'm here, delta H should be this value. When I'm here, delta H 0, therefore, I show it with the term I, not me, Darcy showed it with the I, and we can say that Q equals to minus I times area. And you saw here, actually, this is not equal, this is still proportionality. And to change this proportionality to equality, I have to multiply this term into a coefficient, because here still my equation is not consistent or dimensionally correct. You know what is the dimension of Q? Cubic meter per second, yeah, cubic meter per second. But I is length over length, dimensionless. A is square meter, for example, in SI. Cubic meter per second equals to something unitless times meter square. Therefore, I need a coefficient with this unit to have dimensionally correct equation. And this coefficient is called hydraulic conductivity. Therefore, discharge of liquid from X1 to X2 equals to minus KIA. A is this cross-sectional area. I equals to delta H over delta X. K is hydraulic conductivity. You see, actually, when I said A, this is total area, but we know that, as I told, water moves only from the void area, from the voids, open spaces, not through this solid materials. Therefore, I should correct area to have real, and this coefficient considers that or considers or how can I say, it shows the effect of porosity, actually, the effect of porosity, and also some other things that we maybe do not consider. For example, temperature. For example, if liquid temperature is high or low, its viscosity will change. Therefore, by changing the viscosity, maybe the velocity will change. And okay, it could be considered, it could be hidden, actually, that also could be hidden in this coefficient, and which is very important in groundwater. It is called hydraulic conductivity. Okay, so I know that how to calculate discharge in a soil sample. Discharge equals to minus hydraulic conductivity times I. This value, tangent of theta, shows the loss of energy, loss of head, times area of the sample. Okay, let's continue. This is total Q, entire Q, and it shows the volume of, or volumetric discharge. Okay, but as I told, water does not move through the entire area, just moves through the voids. Therefore, another term which is called specific discharge is or volume flux density is defined as a division of discharge or volume flux by the area, by entire area. Therefore, if we say this is specific discharge, it represents the real amount of liquid that passed through the sample, through the voids. And the equation is simpler. Yeah? Q equals, or specific discharge equal to minus K times I. We know each term. And finally, you know that velocity equals to discharge over the area. But I already adjusted my equation based in here when I calculated net volume flux density. I adjusted my and I get rid of the global area, total area of the sample, just by dividing the specific discharge by porosity. You can find you can find effective groundwater velocity, or the net groundwater velocity. This is the value that water moves, or liquid moves from, or average velocity of liquid when moves it from x1 to x2. So to calculate effective groundwater velocity, which was the first question of this lecture, you need to calculate specific velocity, easily equals to minus K times I. K is not in your hand. K is determined by experiments. For different soil types, we have different hydraulic conductivity. I is it can be derived from the geometry of our system or soil sample. And finally, by division of porosity, is also defined in different ways. We talked in infiltration lecture about how we can measure the porosity, and then you can find effective groundwater velocity, VE. Okay, so let's come back to our question. What is the velocity of water? You remember I gave you this example. I said there is two monitoring wells or piezometers. Water elevation at well 1 is here. Water elevation at well 2 is here. The distance is 1, and the distance or difference between water elevation at this point and this point equals to 1 meter. So how I can find velocity of this liquid? Using the equations that I already said you. So first I'm going to calculate specific discharge. Okay, specific discharge equals to minus K times A. We assume that K, I minus times K times I. We assume that K is 10 for this soil sample. And I, how we can calculate I equals to delta H, either from here or from here you can find delta H. Delta H over delta X, my delta H is 1 meter, delta X is 1000 meter, therefore I equals to 10 to the power of minus 3. And therefore discharge is 10 to the power of minus 2 meter per day, specific discharge. And again, this assumption of the porosity equals to 0.4 comes from the information that we have about the soil in this zone of the soil. Therefore, net or effective velocity would be equal to 2.5 times 10 to the power of minus 2 meter per day. You see how it is small, 2.5, 2.5 centimeter per day. It means that just after a day, this water molecule moves 2.5 centimeter. Look, so how many days or months or years I need when water moves from here to here or passes this 1 kilometer of this soil. So this is why we say that velocity is negligible in the energy equation when we consider the total energy of soil samples, and this is why we use hydraulic head, just hydraulic head, when we are going to find the direction of motion from one point or other point, or we can again conclude that by the law of nature, water flows from high to low energy, and this equals to our hydraulic head in soil mechanics. Okay, any question?